Hi, it's Miss Gray. We are going to go through the 2014 Aqueous Solutions paper today and have a look at how to answer the questions and make sure that the answers we give are in lots of depth and detail so that we can get some good results in the paper. Question 1 gives us a reaction to have a look at. So when chlorine gas is added to water, the equation for the reaction is chlorine gas plus water liquid goes to hydrochloric acid aqueous plus hypochlorous acid aqueous. Part A asks us to write an equation for the reaction of the weak acid hypochlorous acid with water. Question 1 gives us a reaction to have a look at. So when chlorine gas is added to water, the equation for the reaction is chlorine gas plus water liquid goes to hydrochloric acid aqueous plus hypochlorous acid aqueous. Part A asks us to write an equation for the reaction of the weak acid hypochlorous acid with water. When hypochlorous acid reacts with water, it partially dissociates, which means only some of the molecules turn into hydronium ions and OCl- ions. So what we need to make sure when we write this equation is that we use an equilibrium arrow to show that partial dissociation and also to show that it's an equilibrium relationship where both reactions are actually occurring, the forward and the reverse. HOCl is an acid, so hypochlorous acid. When it reacts, it loses the H plus ion and it becomes OCl minus, and that is its conjugate base because it has lost that H plus. The H plus has been transferred to the water molecules, forming the hydronium ions. Writing the correct equation here will give you an achieved grade. The next part of the question asks us to list all the species present when HOCl reacts with water in order of decreasing concentration. So in a question like this, to answer the question, we need to look at our equation that we wrote in the previous part of the question because that gives us a big hint as to what's going to be present in that solution. So what we wrote was an equation for a weak acid. So when a weak acid reacts with water, only some of the molecules do, and it's a small amount. So you still have lots of hypochlorous acid molecules in your solution. You have heaps of water molecules floating around, and then you have a small amount of the ions that were made through the hypochlorous acid reacting with water. So you're going to have a small amount of H3O plus and hypochlorous ions present. You also have water's equilibrium that you need to consider in this question. So water always exists in an equilibrium with itself as molecules, and hydronium and hydroxide ions are always present there. So water has a pH of 7, meaning that the concentration of both of those ions is going to be 1 times 10 to the negative 7 in a neutral solution. So in this case, they're not going to be that concentration. It's an acidic solution, so the H3O plus ions are going to be in a greater quantity than the hydroxide ions that have formed, but they are still always going to be present in the solution when it's an aqueous solution, so we need to factor that in. So in terms of answering the question here, what we need to do is give the order of decreasing concentration. So we're going to have lots of HOCl molecules, hypochlorous acid molecules floating around in that solution, and they are going to be in greater concentration than everything else that's in there because it's a weak acid, it only partially dissociates. Then we're going to have the next highest concentration of H3O plus ions, and that's because for every one HOCl molecule that reacts with a water molecule, it forms one H3O plus and one OCl minus ion. So they're almost in equal concentrations. However, there's a tiny bit more H3O plus because some of that's come from the dissociation of the water as well. So it's only a tiny number, but it's still there, so slightly greater than the OCl minus ion concentration, which is greater than the OH minus, the hydroxide ion concentration, which is there in a very small amount. In the last part of the question, we're asked to justify the order that we've just given. So what we now need to do is just put some words around what we've already figured out. So we really need to think back to that original equilibrium that we wrote and use that as well to help us justify our answer. So the first point that we need to make is from that equilibrium that it's a weak acid, so it only partially dissociates in water, and so the equilibrium lies to the left-hand side of that reaction and it favours the reactants. Therefore, the hypochlorous acid, the HOCl molecules, are present in the greatest amount in that solution. The next point to make is that H3O plus and OCl minus ions are produced in equal amounts in the dissociation of the acid, and there is also a small amount of H3O plus ions coming from the water. So therefore H3O plus ion concentration is greater than the HOCl minus ion concentration. The last point to make is where the hydroxide ions come into it. So if you can use the relationship with Kw, that makes it a little bit easier to explain this bit. So Kw is equal to 1 times 10 to the negative 14, and it's always the hydronium and hydroxide ion concentrations that make that 1 times 10 to the negative 14. So this solution is acidic, so that means that the H0 plus ion concentration is going to be high. So if that's high, the OH minus ion concentration is going to be low, making it the lowest of all the concentrations there. Now, when you're answering this, use those equations. Sometimes it's easier to put them in your answer and draw some arrows to say this bit's this and that bit's that, and that's absolutely fine. And often in chemistry, an equation makes more sense than words, or if you're linking the two together, that's the best way of explaining something. Okay, in part B of the question, we need to look at some pKa values. So I'll just read the question here. Hypochlorous acid has a pKa of 7.53. Another weak acid, hydrofluoric acid, has a pKa of 3.17. A 0.1 mole per litre solution of each acid was prepared by dissolving it in water. Compare the pHs of the two solutions and no calculations are necessary. To answer this, we need to understand a little bit about Ka. So Ka is the acid dissociation constant, and the larger the Ka value is, or the smaller the pKa value is, because that's worked out by calculating the negative log of the Ka. So the bigger the Ka is, the smaller the pKa is going to be. And in that case, the more an acid will dissociate. So if an acid is dissociating more or lots, it's going to produce lots of H3O plus ions and hence a more acidic solution with a lower pH. So if we link that into the question here, hypochlorous acid has a pKa of 7.3. That's much higher than hydrofluoric acid, which has a pKa of 3.17. So HF, or hydrofluoric acid, with the lower pKa of 3.17 is going to dissociate more in water. So the solution that's 0.1 is going to have more H3O plus ions present, which means it will be more acidic and it will have a lower pH. So that's the key idea there. We just need to put that into some sentences to answer the question fully. So let's have a look at how we do that. Okay, so the first point to make in your written answer is what you've just figured out with the values. So HF has a lower pKa than HOCl, therefore HF is a stronger acid than HOCl and dissociates more in water. Because it dissociates more, it produces more H3O plus ions. So therefore, because HF dissociates more, the 0.1 HF solution will therefore have a higher concentration of H3O plus ions than the 0.1 mole per litre HOCl solution, and because as the concentration of H3O plus increases, pH decreases, HF will have a lower pH than HOCl. In part C of the question, we now look at a buffer calculation. So the question reads, an aqueous solution containing a mixture of HF and sodium fluoride NaF can act as a buffer solution. Calculate the mass of NaF that must be added to 150 ml of 0.05 mol per litre HF to give a buffer solution with a pH of 4.02. Assume there is no change in volume. The molar mass of sodium fluoride is 42 grams per mole, and the pKa of HF is 3.17. So there's lots of information there. We need to calculate the mass of NaF using all the other information. So here's how to go about doing that. With buffer solutions, the easiest way I think that you can calculate what you need is to use your Ka expression, which you derive from whatever the weak acid is in the solution. So in here we can write an equation for the dissociation of HF in water, and then from that we can write a Ka expression. Now I've color coded this here just to try and help us work out what bits we are trying to find and what bits we know. So the green, the F minus, that's what we're trying to find out, and that comes, the fluoride ions come from the sodium fluoride that you're going to add to the solution, so that's what we're trying to find out. The blue, the H3O plus, we can calculate from the pH of 4.02. The Ka we can calculate from the pKa given in the problem, and the purple arrow is for the HF concentration, and that's actually given in the problem. So here I've calculated those values. So Ka is 10 to the power of the negative pKa. I get 6.67 times 10 to the negative 4 for that. H3O plus is 10 to the negative pH, and I get 9.550 times 10 to the negative 5 moles per litre for the H3O plus concentration, and the HF concentration was given in the problem as 0.05 mol per litre. So from that, I can stick those values into my Ka expression. So I've stuck with the color coding here, got my Ka value, my H3O plus value, my F minus value is what I'm trying to find, and I've got my hydrogen fluoride concentration there in purple down the bottom. So I need to rearrange that Ka expression now to make that fluoride ions the subject. So if I do that, I can then calculate out what the value for that is, and that equals 0.354. So I've got the concentration of fluoride ions now, but in the problem it asks me for the mass of sodium fluoride. So what I need to do is work out the number of moles of fluoride ions in the solution, and I can do that by using the formula concentration times volume, and I work out that the number of moles is 0.0531 mole. And then from that I can get the mass that I then needed to add to make the buffer solution. So mass is number of moles times the molar mass, and I get 2.3 grams to 3 significant figures as my final answer. So as a rule, you should round your final answers to the minimum number of significant figures given in the problem, and 99% of the time in the level 3 external exams that's 3 significant figures. So that's why I've done that there. For the marking of this question, to get E8, you needed to, in the first part of the question, get all the species correct, put them in the right order, and then have that justification like we wrote in there. So that was one of the E points, and the other E point was just to get that calculation right at the end, making sure your final answer has units on it as well. So those two bits, and you've got E8 in that question. Well done. Now we're on to question 2. Which reads, a flask contains a saturated solution of lead chloride in the presence of undissolved lead chloride. A. Write the equation for the dissolving equilibrium in a saturated solution of lead chloride. Okay, so we've got a saturated solution, so that always contains solid, which is dissolved into ions, and at the same rate that that's happening, we've got those ions going back to being a solid. So we just need to write the equation for that, which shows PbCl2 solid goes to lead ions plus 2 chloride ions, and we need to show that equilibrium relationship by putting that equilibrium arrow in there. The next part of the question says to write the expression for Ks for PbCl2. So to do that, we use what the products are in the top equation, so our lead ions, and we multiply them by the concentration of our chloride ions, and that needs to be squared because there's 2 chloride ions for every 1 lead ion in the original equation that we wrote above that one. In the next part of the question, we're asked to calculate the solubility in moles per litre of lead 2 chloride in water at 25 degrees Celsius and give the concentration of lead ions and chloride ions in the solution, and we're also given a Ks value there for lead chloride of 1.7 times 10 to the negative 5 at 25 degrees Celsius. So remember, square brackets always mean concentration in moles per litre, so the lead and chloride values there, that means concentration moles per litre, so that's what we need to work out. So first thing I would do here is I would go back to what we just wrote, our Ks expression, and I'd have a look at that, and I see there that that is equal to 1.7 times 10 to the negative 5 in the problem. So I'm going to say to let S equal the solubility of lead chloride, and then looking at my equilibrium equation and using that S as the solubility of lead chloride, I'm going to say that lead chloride is S, lead is S, and the chloride ions are 2S. And the reason they're 2 is that there's 2 chloride ions in the equation. So for every lead chloride that dissolves, you get 1 lead ion and 2 lead chloride ions. So from that, if I substitute those S's into my Ks expression, I get Ks is equal to S times 2S squared. And if I expand that out, I get 4S cubed. So now I can do some maths, and I can see that Ks is 1.70 times 10 to the negative 5, so 4s cubed equals that, and then if I rearrange that and solve it, I've worked out my lead chloride solubility, which is 0.0162 moles per litre. Now the question also asked us to find the ions concentrations, so I can do that here. It was a one-to-one relationship in the equilibrium reaction, so the lead ion concentration is going to be the same as the lead chloride, which is 0.0162, and for every 1 lead ion that was forming, I had 2 chloride ions that were forming, so that's going to be double that, and that will give an answer of 0.324. Part B of the question states, a sample of seawater has a chloride ion concentration of 0.440 moles per litre. Determine whether a precipitate of lead chloride will form when a 2 gram sample of lead nitrate is added to 500 mils of the seawater. And the Ks of lead chloride is given again, which is 1.7 times 10 to the negative 5, and the molar mass of lead nitrate is 331 grams per mole. To answer this question, what we need to do is calculate an ionic product, which we use the same working for Ks for, and when we get a value for the ionic product, we need to work out if it's bigger than Ks, then the solution is going to be more than saturated, so a precipitate is going to form, and if it's less than Ks, then no precipitate is going to form. So in the problem, we're given a concentration for the chloride ion in the seawater, which is 0.440, and we need to actually use the rest of the information to find out the lead ion concentration. So what we need to do that is we need to go, the number of moles of lead ions is mass over molar mass, so 2 divided by 331, and we get 6.04 times 10 to the negative 3. Then we can use that number of moles to find the concentration of the lead ion concentrations using the number of moles divided by the volume. Now just remember to put your volume into litres, so the 500 mils is half a litre, and that gives us a concentration of 0.0121 moles per litre. So once we've got those concentrations, we just need to substitute them into our ionic product value, so or expression. So we do that here, and we get an answer of 2.34 times 10 to the negative 3. So we just need to now compare that to our Ks value, and you can see there that it's much bigger than our Ks value, so that means that a precipitate is going to form, and we just need to write a sentence to clarify our understanding there. So IP is greater than Ks, therefore a precipitate will form. Okay, now the last part of the question, which is C. This is about solubility, so let's have a read. The solubility of zinc hydroxide can be altered by changes in pH. Some changes in pH may lead to the formation of complex ions such as the zincate ion. Use equilibrium principles to explain why the solubility of zinc hydroxide increases when the pH is less than 4 or greater than 10, and no calculations are necessary. To answer this question, the first thing we need to think about is the zinc hydroxide solubility equilibrium, and I'd write that first so that you can keep thinking back to what's going on as you go through the question with that. So that lives in an equilibrium where there's solid and ions there. So something's got to happen to either side of that equilibrium for the solubility to change. So the first part that I want to go with is when the pH is less than 4. So the first point to think about here is that if the pH is less than 4, then the solution is acidic. So if the solution is acidic, you get a high concentration of H3O plus ions. They are going to react with hydroxide ions. So they're going to start reacting with the hydroxide ions in the solution, and what that's going to do to their equilibrium is it is going to shift it towards the right. So as it shifts to the right, it's going to try and replace the removed hydroxide ions, and it is going to mean that more zinc hydroxide is going to start to dissolve into those ions, and the solubility of it is going to increase. So that's what you really need for the first part of that. If we get to the second part of it, the pH now is greater than 10. So that means that it's basic and there's a high concentration of hydroxide ions present in the solution. So in the actual question, there was a big clue here about what was going to happen when there was excess hydroxide ions, and that is that the zincate ion is going to start to form. So the zincate complex ion will form, and that's going to remove, once again, hydroxide ions from the solution, which there's an excess of anyway, so that's not going to make too much of a change. But in the process of doing that, it's actually going to remove zinc ions from the solution as well. So the same thinking as before is going to apply. The equilibrium is going to shift to the right even further, and when it does that, the solubility of the zinc hydroxide is going to increase because more of it's going to dissolve to replace those zinc ions. So you need to have both parts there, but both are along the same lines. You just need to think, what's this going to do to the equilibrium? Oh, it's going to do that. Explain it, use an equation, and then you're away. Okay, so looking at the mark schedule for that question, question 2, you needed to, for E8, answer both parts of the question correctly and have all your calculations in the first part correct and full explanations in the second part explaining what was going on in the acidic and the basic pHs. So both of those parts got you the E8 for that question. Okay, last question, question 3. So this is a titration question, and it tells us that a titration was carried out by hydrobromic acid, HBr, to 20 ml of aqueous methylamine CH3NH2 solution. Then it gives us an equation for the reaction and a Ka value, and a look at the titration curve for the titration, labelling points A, which is a buffer zone, and B, which is the equivalence point of the titration. So they're labelled on the graph, and you can see that CH3NH3 plus is the acid there, so that's going to be the conjugate acid of methylamine. So there's quite a bit of information given to us at the start here. Part A asks us to explain why the pH doesn't change significantly between 5 to 15 ml of HBr being added. So that's around point A on the curve, and it says to include any relevant equations in your answer. So if we just think about the original titration reaction, methylamine is reacting with HBr and it's forming methylammonium and bromide. So you can see there that as that proceeds, you're going to get less CH3 and H2, and you're going to get more CH3 and H3 plus forming. At point A, these two species are in approximately equal concentrations, so about half the CH3 and H2 has reacted, and you've got a buffer mixture there. What's important about that is that as the HBr is being added and there's more H3O plus in the solution, it's becoming more acidic. Well, you're adding more H3O plus to it. The CH3NH2, the methylamine, is actually reacting with that and neutralizing it, and it's becoming CH3NH3 plus and H2O. So as that happens, that's neutralizing any H3O plus that's being added to the solution, so the pH of the solution doesn't change significantly. In part B, the question reads, the aqueous methylamine CH3NH2 solution has a pH of 11.8 before any HBr is added. Show by calculation that the concentration of this solution is 0.0912 moles per litre. Okay, so the first thing here to have a think about is that methylamine is a base, so we need to write an equation for its dissociation in water. So methylamine plus water goes to methylammonium plus hydroxide. And then from that, because it's a base, we can write a Kb expression. And in that Kb expression, we've got the concentration of the methylamine there, which is what we're trying to work out. So next step, I would calculate a Kb value. So in the question, we're given our Ka value, which is 2.29 times 10 to the negative 11. So I can go Kw divided by Ka, and I get my Kb value there of 4.367 times 10 to the negative 4. Once I have that, I can make an assumption that the methyl ammonium ion's concentration is going to equal the hydroxide ion concentration. So I can simplify that top line there of my Kb expression to just hydroxide squared, and then I can substitute in my values. At that point, I need to know my hydroxide ion concentration, so I've just worked that out on the right hand side here. So from the problem, we were given a pH of 11.8. I can get my H3O plus ion concentration from that, and then from that I can use the relationship of Kw over H3O plus equals hydroxide, and I can calculate my hydroxide value from there. So then I can go back and substitute that in on the other side and divide that by my Kb, and I get that concentration, which is 0.912 moles per litre, which matches the concentration at the start, so it must be right. Yay! The first part of question 3c asks us to write the formula of the 4 chemical species apart from water and hydroxide that are present at the point marked B on the curve. So point B is the equivalence point of the titration curve. So what that means is, in terms of the titration reaction that has gone on, at that point everything in the equation is as written. So in this case, it means that equal moles of the methylamine have reacted with the hydrogen bromide and formed equal moles of the two products there. So they have completely reacted, so there is no more of them there, and so we just have CH3NH3 plus and bromide ions from that equation present in the solution. The question gives us a big hint because it says 4 species. So one of these two ions must be going on to react and with the water in the solution, and CH3NH3 plus, that's the conjugate acid of the methylamine, so that's going to be what it is. So if we write an equation for that, we can see that it then forms a small amount of methylamine again and some H3O plus ions. So there are 2 missing ions, or one's a molecule, one's an ion. So in terms of answering the question, the 4 species that are present are CH3NH3 plus, Br minus, CH3NH2 and H3O plus. The next part of question 3C asks us to compare and contrast the solution at point B, so that's the equivalence point, with the initial aqueous methylamine solution. In your answer, you should include a comparison of the species present and their relative concentrations, a comparison of electrical conductivity linked to the relevant species present in each solution, and equations to support your answer. So when it says relative concentrations, we just need to say what's bigger than what. We don't need to give actual amounts. So that's a little bit easier than having to calculate everything out. So let's start off with the methylamine solution. So methylamine is a weak base, and weak bases partially dissociate in water. So we should really write an equation for that because it's asked us to write equations to support our answer. So I've got that one here. So that's just showing its dissociation in water with an equilibrium arrow. Because it is a weak base and only partially dissociates, it produces a relatively low concentration of ions. So it's not going to be a great conductor. So I've got there that it'll be a poor electrical conductor. And I've linked that to those low concentration of ions in that sentence there. The last thing we need to do is give the relative concentrations of the species present. So we're going to have the most of the methylamine because that's only partially dissociated, so only a small amount of it's turned into ions or reacted with the water. Then the next biggest concentration is hydroxide ions, and that's being formed in pretty much equal amounts as CH3NH3+. It's just that there'll be a tiny amount from the water as well. If you'd put equals there for the two ions, you'd get away with that as well. It's more correct to say greater than, so I've put that here. So that's greater than CH3NH3+, which is greater than the H3O+ ions, which has come from the water because it's an aqueous solution. At point B, we now need to have a think about what's going on there. So point B is the equivalence point that we discussed earlier. So it essentially is a solution of CH3NH3+ and Br- ions. So it's an acidic salt solution of those two ions. Therefore, there's a relatively high concentration of ions, so it's going to be a great electrical conductor. CH3NH3+ is a weak acid, so a small amount of that is going to dissociate in water. So we just need to write an equation to show that we understand that, and that's going to form CH3NH2 and H3O+ ions. So because it's forming H3O+ ions, it's acidic. Once we've got that figured out, we just need to give the relative concentration of all the ions in the solution. So highest concentration is our bromide ions because a small amount of the CH3NH3+ has dissociated. So that will be next, followed by our H3O+ ions, which are a tiny bit higher in concentration than CH3NH2 because of water. And then we have a small amount of hydroxide ions present, which is also from the water solution. So that is our order there for the last part of that question. Now, in terms of marking this last question, if you gave a correct answer and a clear method in your calculations in the first part, and then you gave full explanations in the second part as to what was going on, what ions were present and the concentrations in the right order, then again you would have got an E8. So it's not too difficult to do this. You've just got to think through the steps as they go and make sure that you've fully answered each question, giving what the question has stated in your answer as you go through it. These are the cut scores or the grade boundaries for this paper in 2014. So to get achieved, you needed at least 8 marks in the paper, and to get merit 14 and excellence 19. So that's where the grade boundaries lie. The link underneath that there is the link through to the NCEA website if you'd like to use that. That'll take you through to the Aqueous Solutions papers, so you can access different years or answer schedules there as well. Thank you for listening, and I hope you found this helpful.